So these airplane type problems, um, I typically will not put too much emphasis on these, and I've called this enrichment, or in other words, it's not going to be on the test, because I think that um, the actual physics behind this, when we go and solve problems, really only the first part of the solution ends up being really physicsy, and the rest of it is a lot of geometry, using the sine law and the cosine law, just a lot of calculations there, which is more like just computational and um, takes a long time. So like the ratio of how much physics you need to know versus how much computation you need to do, I don't really like that ratio for my students too much. So I think it's still good to know the concepts. So I'll show an example here, and I'll put one or two as an option on the problem sets, but I won't really ever test you guys on this. So I'll talk about it though. So airplanes, there are 6 terms I've listed at the top there. The ones on the left are scalars. The ones on the right are vectors or related to vectors, so they have direction. So air speed, that word stands for how fast the airplane would go in still air. So if there was 0 wind at all to affect this airplane, then what speed would it be able to fly at? And then the wind speed would be the speed that the wind is blowing. So that's going to move the air, which is going to affect the airplane's motion. And then the ground speed. So the ground speed is the speed of the plane relative to an observer at rest on the ground. So people in the control towers monitoring all those planes, they're going to see the ground speed of all these planes. And that's going to be some combination of the airspeed and the wind speed. But then we're probably more interested in the velocity side of things because we care a lot about the direction that these planes are going. So I'm going to use the word heading to represent the velocity that the plane would go in still air. So that's basically just the air speed along with which direction it would go if there was no wind. And then wind azimuth is just a term used for the direction of the wind. And then ground velocity would be the velocity of the plane relative to an observer on the ground. So the one formula that relates these 3 concepts is written in the box there. So you take your heading as a vector, and then you add it to the wind velocity vector, and simply the sum of those 2 is going to equal the ground velocity. So the heading, I often say that's which way the pilot is going to aim the plane. Okay, which way they're going to aim the plane, plus the wind. So the wind's going to adjust it. And after you add them together, that's the direction the plane will actually end up going. That's called the ground velocity. And you'll find that you don't usually get 2 full vectors and just solve for the third one. If that were the case, then you could just use vector addition or subtraction from the previous slides. Maybe an online calculator will do that for you. But in these situations, normally you get the magnitude of one variable, the direction of the other variable, and you don't usually get 2 full complete vectors that you have to work with. And that's why it turns out, at least in my opinion, that the fastest way to do a lot of these problems ends up being to use geometry. So to draw a triangle out and to calculate missing sides and missing angles using sine law and cosine law. So here's one example. An airplane's destination is 1,200 kilometers west, 20 degrees north of the plane's current position. The plane can fly at an airspeed of 800 kilometers per hour, and the wind velocity is 50 kilometers per hour south 40 degrees west. Determine the direction the plane should head and how long will it take the plane to get to the destination. So first of all, I'm going to write out my givens in the formula. So The only thing I know both the magnitude and direction for is the wind velocity. So the wind velocity, I have 50 kilometers an hour and south 40 degrees west. However, the heading, I only have the magnitude of that one. I only have 800 kilometers per hour. I don't know the direction though. And then the ground velocity, so it says the airplane's destination. That's a displacement they give, right? 1,200 kilometers with the direction. That's a displacement. That's not the velocity. But the velocity is going to be in the same direction of the displacement. So I can actually use the direction here. But I don't actually know the magnitude of that velocity. So that's what I mean by some of these terms you have, you don't have the full information. You may have one of the two things of the vector. So I think the best way to do this is actually to draw out a triangle and just solve for some missing sides and angles. So let me show you how that works. I'll just recopy the formula. So it's the heading plus the wind velocity is going to equal the ground velocity. And I'll copy down my numbers again, 800 kilometers per hour, but I don't know the direction. And then 50 kilometers an hour. I do know the direction of the wind. And then ground velocity, I don't know the magnitude, but I know the direction. Okay, this is how I would approach drawing a diagram. I would start by just putting a dot where the airplane is currently. So that's just going to be where my airplane is currently. And then I'm going to draw a line in the direction of where the destination is. Okay, so I'm gonna draw the destination basically. So that's west 20 degrees north. So I'm just kind of estimating here. That might be about 20 degrees. So I'll label that. I'll label the angle. So the destination is somewhere along that line. Okay. So now I'm gonna draw the wind. Now I'm gonna draw the wind. The wind is 50 kilometers per hour, south 40 degrees west. So I'm gonna draw it, let's say this is my destination at the end of that line there. So I'm actually gonna draw the wind pointing right to that dot. So something like this. This will be my wind. And that's 50 kilometers per hour. I'm going to label some things here. DEST for the destination. The destination somewhere along this straight line. See, what these arrows I'm drawing are actually velocities, so it's not actually the displacement I'm drawing. So the destination is somewhere that way. All right, now the last thing I'm going to draw is the air velocity, or the heading. Which way should this plane head? And it should head basically from where the plane is to where the tail of the wind left off. Try to draw a straighter line here. Nope. So that is where the plane should head. It is 800 kilometers an hour. So essentially, I'm gonna have the plane head that way at 800, but then the wind of 50 is gonna push the plane to kind of adjust its course to create this resultant ground velocity, which I will just label as V. That'll be my ground velocity. Okay, one more thing I have not yet labeled that I know the information for is actually the angle of the wind. It says the wind is south 40 degrees west, so I can label that angle. So that's south, and this would be 40 degrees. Okay, next I'm going to switch colors here. So I'm going to use red, I suppose. What am I supposed to find out? So part A, determine the direction that the plane should head. So part A is asking me to get this red angle here that I've just drawn. Okay, so maybe I'll call that theta, the entire red angle there. So it's going to be something that's bigger than 20 degrees based on this diagram. And I'm also asked to find how long the plane will take to get to the destination. So that's a time. So I'm going to have to find out. I'm going to have to find out the overall velocity in order to eventually find out the time. So I need to use geometry using this triangle here to try to find out that missing angle and this missing side. All right, so how does that work? Well, you just gotta think about all your geometry skills, use any tricks you know. So something I see is a Z pattern. I see a Z pattern. I will draw it in, what color am I? Yellow. I'll draw the Z pattern in yellow. So using this 20-degree angle here, zipping across the ground velocity, and then I'll draw another horizontal line here, completing this Z pattern, meaning that this portion of the angle is 20 degrees. And then if I take my yellow dotted line, and then that vertical dotted line, well, that makes a 90-degree angle. So I've got a small right angle triangle there, which I can use to find out this angle. So I'm going to zoom in here. So that angle I just labeled, that would be 180 degrees minus 40 degrees minus 90 degrees, which would end up being 50 degrees. So altogether, the angle on the left there is 50 plus 20, which is 70 degrees. Got a 70-degree angle there. All right, what else? Okay, what I'm going to do is label some stuff in green now. So I'm going to go for this little chunk here. Let me call that, I've already used theta in this diagram, so let me call that, I'll call it alpha. All right, I am going to find angle alpha because I can use the sine law to do that. Alpha is opposite to side length labeled 50, and then the 70 degrees in yellow there that I've just identified, that is opposite to the 800 side. So I actually have 3 out of 4 values there. I can use the sine law to get alpha. So it looks something like this. Sine of alpha over 50 kilometers per hour equals sine of the 70 degrees over 800. And then I do all the mathematical steps for the sine law. So it's going to end up being the sine inverse of 50 times sine 70 over 800. So just multiplying 50 to both sides and then taking the sine inverse, that'll get me the angle there. So I'll pull up my calculator. And that is giving me 3.4 degrees. So my diagram's not that to scale. It's actually a nice small angle there. Okay, so that is my angle alpha. And my angle theta that I've labeled in red, that would simply be 20 degrees plus alpha. Which would be 23.4 degrees. That's only go to the nearest whole number though. Okay, so that's actually part A answered. The answer is 23 degrees. Or, well, the full answer would be west, 23 degrees north. Okay, part B. Well, this is going to require me to find the missing side labeled V there. And I can use sine law again, or I can use the cosine law. But I'm first going to need to know this last angle here before I can actually complete it. So I can get that actually because I know all the angles in this triangle, all the interior angles have to add up to 180. So I just take 180 and I subtract all those angles I have written there. So 180 minus 40 is 140, and then minus 70 gives me 70, and then minus 3.4 gives me 66.6. That's an ominous number. Okay, so that was 180 minus all these other angles in there. Okay, so with this triangle, that means that the total angle up top there is 40 plus 66.6, so 106.6. So I can use the sine law again. This time I'll say sine of 106.6, so that top angle, over the magnitude of V equals, now I choose another pair. I'll go with a 70 degrees again, which is opposite to 800. And I can go ahead and solve for the velocity now. So you do some cross multiplying and dividing stuff, leaving you with 800 sine 106.6 over sine 70. So that's giving me 815.9 kilometers per hour. That would be to 2 sig figs. I kept a couple extra digits because I'm not done yet. I need to find the time. That's the last step of this whole thing. And I'll do that just by using the average velocity formula. So the velocity, which we now know to be 816 basically, will be the displacement divided by the time. So we can rearrange this. So time will be displacement over velocity. So the displacement is 1,200 kilometers. The velocity is 815.9 kilometers per hour. So we divide those, and I get 1.5 hours, 1.5 after I've rounded to 2 significant digits. Okay, so as you can see, this took a really long time. Most of it was geometry. The only real physics was drawing the diagram properly in the first place, which is not so simple. But a lot of time was spent on this geometry stuff, so that's why I'm not really going to put it on our physics test. Just the proportion of ratio to calculations is too low. But it's still good to know if you're planning to do physics, if you plan to continue on with that in university and whatnot. And I'll add one or two in a problem set. It could be one of the questions you draft if you're comfortable with it.